Hi everybody and welcome back. In this lecture we will implement oversampling. The following four libraries are necessary. Pathlib to create the path object necessary for our dataset, PyTorch to create the actual sampler, NumPy to compute the fraction between the tumor-free and tumorous slices, and of course the lung dataset. Above all, we need to create our train dataset by using the lung dataset class, to which we pass the path to our preprocessed data, in my case preprocessed/train, and as this is simply an exemplarily lecture, no data augmentation. We now loop over this dataset and store for each label slice if a tumor is present in there or not. To do so, let us define an empty list called target list and then loop over our train dataset. As we don't need to access the single CT slices, let's use the underscore as loop variable to indicate this. Inside the loop, we can now check if at least one tumorous pixel occurs within the current label. Therefore, if numpy.na label is true, we add a 1 to our target list. If that is not the case, and hence all pixels are 0 in the current label, we append a 0. Please note that running this cell might take some minutes. We can now use numpy.unique to count the unique values within our target list. Note that you have to pass return underscore counts equals to true to get the actual numbers. Let's directly have a look at it. As you can see, there are about 13k slices without a tumor and only 1437 slices that actually do contain a tumor. If we now divide these values by each other, we obtain the fraction f. It visualizes that there are about 9 times more tumor-free slices. Let us now create another empty list called weight list, which will store the weight for each sample. We therefore loop over our target list and append the weight 1 to our weight list if the target is 0. Else, we append our pre-computed fraction. Based on this waitlist, we are now able to create the sampler. In fact, we want to use the weighted random sampler, which is accessible via torch.utils.data.sampler.weightedRandomSampler. It accepts at first a waitlist and next its length. That's all. This sampler makes sure that our network sees as many slices with a tumor than without a tumor during training. We are now ready to define the data loader. Let's use torch.utils.data.dataLoader, to which we at first pass the train dataset, next the batch size, let's use 4, and last but not least, our predefined sampler. Please note that it is not possible to pass both shuffle and sampler. As we will never use this particular train loader for training, we can skip passing the numBrookers argument. Let us now loop over the train loader and print the sum for each label in the current batch. To do so, we need to compute the sum along axis 1 to 3. When we now run this cell, we should observe that around 50% of all labels have a sum larger than 0. Perfect! We can observe that most of the batches have at least 2 tumorous slices. Some of them even have 4. To finalize this lecture, let's take a look at the output produced by a data loader without a sampler. To do so, we simply copy the 2 statements from above and delete the sampler. Wow! This shows that most batches do not even contain 1 tumorous slice. Therefore, we can state for sure that our implementation of oversampling works. Awesome! And now I hope you have fun working on this project. Thanks!